To our Reproducing Kernel Hilbert Space Seminars. Our expert speaker today is Jean-Marc Mercier, who is the head of the research and development of MPG Partners, a French company in the industrial sector, and especially specialized in risk management. Dr. Mercier is a mathematician and software developer, business analyst, consultant, having more than 20 years in research and development. And he has a PhD in applied mathematics in Bordeaux University. After that, he has his own career in the European Research Program. And also Dr. Mercier started in 2005 a research program of his own concerning the curse of dimensionality, and this led to develop a framework which is known as CodePy, using the reproducing kernel Hilbert spaces and its methods and applications in many fields, especially in mathematical finance. So we welcome our distinguished Professor Mercier, and today is going to talk on the kernel methods, applications, promises, and open issues, and we all like to listen to him. So you can start.
Okay, so thank you very much for this introduction, Omar. And so just to precise a little bit, I'm working in a consulting firm named MPG, and so the field of specialization of this firm is finance. So it means that today I'm much involved in mathematical finance. So this is the field of my industrial application. So as Amor kindly presented me, so I came to kernel method some 20 years ago through the prism of partial differential equation, where these methods are very efficient, and I will have some word about partial differential equation or mathematical physics, let's say, and kernel methods a little bit later during this talk. But what happens is that after using this method for partial differential equation, we realize that this method are also very performing in other fields, in particular in statistic fields. And I will focus today a lot on machine learning and artificial intelligence topics. However, the point for kernel methods is that this method have some particularities, and it means that we need some dedicated software to use this method properly. And unfortunately, it does not exist today a professional dedicated framework to kernel methods. So what happened is that 4 years ago, using this method for industrial projects, we started to build our own kernel library based on my experience on partial differential equation and kernel methods. But the name of this library is CodePy, kindly introduced by Omar at the beginning of this talk. But the point is, so all what will be presented during this talk has been realized with this library, but it's developed by very small research and development team. So this framework can't compete with big library like TensorFlow, PyTorch, that are dedicated to neural network in terms because we lack resources for maintenance and evolution of this library. So as you have understood, the main goal of this talk is to provide a feedback on kernel methods usage in both research and industry based on our own experience using these methods. So let's come to the plan of this talk. So in the first step, we will focus on machine learning. Machine learning means predictive machine with uncertainty quantification. Yes? Is there some question? Can you hear me?
Yes, no, I guess I didn't. Hoja's microphone is open, so you can continue.
Okay, sorry. So, so we will first consider kernel methods as predictive machine. Predictive machine means interpolation, extrapolation algorithm. Why looking to kernel methods under this particular look? It's because the main competitors of kernel methods are neural networks methods. So neural networks comes from predictive, from machine learning. So we want to benchmark also these methods with neural networks. So after reviewing a little bit machine learning, we will have some word about the link between kernel methods and partial differential equation and mathematical physics. So I will give you my feeling regarding this method and their use for numerical simulation. And then we will go back again to statistical learning algorithm, because we also develop methods that are kernel based, that are quite efficient for fields of statistical learning that are quite trendy today. It means generative method. We could speak also about large language model, and I will have also some word about reinforcement learning, but with kernel methods. So it means that if you need some keyword, I will speak in the first part about supervised learning or unsupervised learning. This means clustering method. I will also have a particular focus on large data sets, because the large data set is the weak point today for kernel methods. Concerning partial differential equations, the keywords are mesh-free methods and particle methods, where kernel methods are very handy to tackle this kind of approaches. And concerning statistical algorithms and generative method, we'll talk about encoders, decoders, and reinforcement learning. We will talk about methods, algorithm, methods like arithmetic Q-learning. These are classical methods, but we can let's say re-engineer them with kernel approach, and then we can benchmark different approaches using this approach. So let's have a focus on what is a predictive machine. A predictive machine is something. So the first point is that when it comes to machine learning, there exists a lot of algorithms that are capable to give a prediction. You have, for instance, trees-based algorithm. You have also neural networks. You have kernel method is just one among maybe 100 different methods. So it's important for us, in order to benchmark all the methods, to have a general framework in which every method can fit. And the general framework can be described as follows. It means that you define you define a function that is a function of a variable that is called z, that depends on a set of parameters. Whatever parameters are, they can be, they are called weights for neural networks. You have also the equivalent for trees and so on. And I will precise in another slide what are the set of parameters for kernel methods. So, when it comes from machine learning usually are considered as extrapolation or interpolation procedure, and the fitting procedures consist in fitting the set of parameters that are called theta in this notation to a training set. A training set is a couple of variable x and function values f of x. So it may have very different let's say space dimension. And when you say that a method fits a data set, it means that you're trying to solve a minimization problem having this form, and it's a very abstract one. When you try to minimize an error on the data set, and I'm sorry, there is a little typo here that it should be a x instead of a dot. And you give yourself an error measure and you try to minimize the target function to your data set according to your error measure. So you can see, I gave you a very simple example at the bottom of this slide. You just have a function of x, and the function of x is a brave sinus function. And what you want, once you have fitted your parameters, you would like to see what happens on unseen data. So here, at left, you have your function, your data set, your training data set, and at right, what you want to test is how much, when you extrapolate far beyond the training data set, how will behave your prediction. So this mechanism of interpolation and extrapolation procedure is at heart of machine learning first, because here in this example, instead of considering x in the real line and f the x as a function, you can also consider x as, let's say, picture, or you can consider x as videos or songs, and f the x can be label, and you can say you can fit, for instance, a label for pattern recognition. If you have image of cats and dog, you can consider that f of x is also is a label. So this is the link between machine learning and functional and representation of function. They are the same things. The real difference is that in machine learning, usually the set Z belongs to a very high dimensional space. But this is at heart of all numerical approaches, and especially in mathematical physics, when you try to simulate physical phenomena. So I would like to provide here first some let's say kind reminder on kernel methods. So the first one concerning kernel, that is based on a kernel function, and kernel function is there is a difference between kernels that are used on kernel methods and kernels that are used also on neural networks methods, because for kernel methods, we are always considering symmetrical function, symmetrical kernel function. And so in the list that is here, I pointed you out the kernels function that I'm using on a frequent basis. And the first, this is some kind of zoo of kernel that I'm using quite frequently. So the first one that are very important because they are used to as bricks to build the other as what we call translation invariant kernel. These are kernels that have the following form. They are built on a function taking the difference of your input data. For instance, the most classical one is a Gaussian kernel that is written as follows. So, but one observation is that you have a lot of other kernels, translation invariant kernels that are used. For instance, you have Matter kernels. You have also kernels that are very close to, if you know a little bit the machine learning and neural networks field, that are very close to ReLU function, or but the only difference is that we are only considering symmetrical function. So with this setting, quite interesting and universal representation of kernels are the representation of kernels as feature maps. It means that if you give me any kernels, you can have this representation of a kernel as a scalar product between two functions that are called feature maps. So, and another quite interesting feature is that you can also take a power of this feature map, and you will still have an acceptable kernels for units. So once you have built all this, the two first points, then you can do a little. You can go a little bit beyond and do what we call kernel engineering. If you have two kernels, you can add them, and it will still be an acceptable. When I say acceptable, I mean positive definite kernels. So you can, and I will explain a little bit below what are definite positive kernel. So you can add this kernel, you can also multiply them, you can also take convolution, it will still be an acceptable kernels. And this kind of engineering is quite important to fit a kernel to a particular problem. And you have also more sophisticated construction of kernel. You can take also vector version of kernel. It means that you consider several kernel and take a norm that is compatible with kernel engineering. It will still be an acceptable kernel. You can do also some little things that are usually used for in the neural network community, that are convolutional kernels. They are the equivalent of convolutional networks. But you can do also some other some funny things. You can also deal with Fourier type kernels, and all these kernels are quite important to master when you tackle a new problem, in order to choose and to pick up your kernel to a particular problem. So the next notion that is quite important for kernels are gram matrix. Gram matrix is just if you consider two sets of data. So when I quote small x, it means that is the vector. When I use capital, it means a matrix. So a matrix is just a collection of vectors for me, just a collection of points. So you can define a gram matrix as a an evaluation of the Cartesian product of two data sets. And this is a matrix, and it's called the Gram matrix. And the property, so I will not enter into technical details concerning positive definite kernels. The only point that is very important to note in this talk is that if you consider a positive definite kernel, it means that the Gram matrix is an invertible, symmetric, because it's symmetric definite positive, it will be always invertible, at least in the least square sense. So another quite important notion for kernels are normalization map. When you consider a kernel like the Gaussian one, you need first to fit your data in order that your Gaussian kernel can leverage its regression power, let's say. So we use normalization map, and the first purpose of normalization of maps for kernels are to fit data to kernels. But there are also hidden features of these maps. They can also be here to control the support of the function that you try to model. So this never forget that you need this map, and this map can be quite annoying when you deal with kernel, because you need first to fit this map with data in order that they fit their own parameter, and then you can use your kernel. But if you change a little bit your data set, you will change the map and you will change your kernel. So it can be sometimes a little bit quite tricky, the impact of these maps. But usually we use for one kernel, we know that this map is usually fit to one kernel. So another quite important notion for kernels are distances. Distances between 2 points. It's called also similarities in the literature. It just gives you this formula that gives you the similarity between two vectors. And you have also another notation that computes the distance, this time not between two vectors, but between two sets of points. So the distance between two sets of points is called also, I call this distance discrepancy functional, but it's known in the literature as maximum mean discrepancy functional, and it comes from a paper from Gretten, Smola, and Sholkov. It's a 2008, I think. So now let us focus on kernel methods. So first thing is to notice is that the set of parameters for kernel methods is quite simple. The set of parameters of kernel methods is just a matrix. So here, theta is a matrix that depends on your input data set. So it's, let's say, n, and I've taken the subscript y to indicate that somehow y is also a hidden parameters, and it takes also the dimension, obviously, of the functions that you are trying to interpolate or extrapolate. But it's a very simple and quite nice expression. And in particular, please notice that you can separate somehow kernel predictive machines into two parts. The first one is a linear operator that is acting on the second part, that are somehow parameters dictated by the function that you try to model. But it means so so it tells you two things, this very simple formula, that you have somehow a dual representation of kernel operator as an operator acting on a set of parameters, and this operator is just the matrix multiplication. So the second point is that the main burden for kernel methods are bare by linear algebra software. And that's a good news, because usually linear algebra software are very optimized software. So we benefit of the leverage of years of development on linear algebra here for kernel methods. So now let us go to the mechanism of fitting. So fitting, when we are speaking of fitting a kernel machine to a function, it means very simply that we are inverting a matrix. And here too, the linear algebra software are very efficient to invert matrices, and these are gram kernel matrices, so they are symmetric, positive defined, and this is usually linear algebra software are very performing to solve this, to invert this kind of function. So indeed, to a kernel predictive machine, fitting is just a matter of matrix inversion. So it means that and in particular, what is important to notice for kernel methods is that these are, to my knowledge, one of the few methods, and I think they are almost the only methods that are capable to have to provide error bound on the evaluation procedure. It means that you have this kind of error bound that you can. We could also work with LP. It will work the same way. This kind of estimation are very important. They are very important for several reasons. They are important for research first, because when you have this kind of error bounds, it means that you can enter into convergence analysis of the methods that you are developing. And I think I don't know other general extrapolation procedure that are capable of providing such error bound, and in the sense that these error bounds are also computationally tractable. So they are quite so it's a quite handy tool for research. But it's also an overall very important for industrial project. Why? Because when you are dealing in an industrial context, you need what is called explainability. When you do a prediction, that is an interpolation procedure on a function, you are acting like an oracle. And the oracle, okay, this kind of error bounds can tell to your clients, we are in industry now, to your clients, how confident you can be providing a prediction. And indeed, what is quite interesting in this kind of error estimation for kernel method is that in a particular case, it means if you take the two set x, y equal to x, and epsilon equal to 0, the role of the parameter epsilon here is to provide some smoothing effect if you work noisy data. But if you don't work on noisy data, you can take epsilon equal to 0. And if you take y equal to x and epsilon to 0, you have directly what we call reproducible properties of kernel method. It means that your kernel method will do 0 error or your training set. So it's quite important for audit purposes. Sometimes it can be also a problem, because if you are dealing with noisy data, this mode of working with kernel methods, that is a pure extrapolation method, can overfit. And you will overfit. I'm not sure that you are familiar with the concept of overfitting. So, but you will have the same kind of problem with every method, and in particular for kernel methods, for in the extrapolation regime. So another quite and very important observation of kernel methods is that with kernel methods, you can define very simply the gradient operator. So it's not the only method that is capable to define a gradient. But for kernel method, it is very important to notice that it is really the same structure that for the prediction algorithm, or the prediction construction. It means that you have only a matrix that you multiply with your parameter. It means that you can have not only the gradient of any function, but you can see with kernel method gradient as a matrix that is an operator acting on some parameters. And this is a very important observation, because if you can take, for instance, the gradient as an operator, then you can take also the transpose of your gradient, and you can call it the divergence. And if you multiply now your divergence, that is a matrix, with your gradient, you have what is called the Laplacian operator, and so on and so on. Indeed, you can construct the whole zoo of differential operator for any purpose for partial differential equation. And most interestingly, you can invert them. If you can define the Laplacian for kernel method is simply a matrix, and it's a symmetric definite positive matrix. So you just invert it, and you have a solution to the Laplace problem very easily. And that's a quite strong point for kernel methods. So now I've talked about let's say the strong point of kernel methods. Let's go now to the dark side of the moon, if you don't mind. The first point is that we should have a closer look to the fitting procedure of kernel methods. So I recall you that to compute the set of parameters, you compute a gram matrix, you invert it, and you multiply this invert matrix by a function, by another matrix that represents your function value. So the first remark is that if your data set, it means that your matrix is big. It means, so for instance, if you have a data set that is more than 50,000 points, then in terms of memory storage, it starts to be quite heavy. So because the memory storage will be the square of your data set size. And if you want to invert it, it will be a cubic function. So it means that basically in the extrapolation regime, you can't handle large data set. Large data set, I mean data set having billions of points. So this is quite problematic for kernel method. There exists solution to my knowledge, there are two big families of approach to tackle the large dataset problem for kernel machine. The first one are clustering methods. So clustering methods, let us review a little bit how they work for kernel methods. So I'll recall you that the error estimation of kernel methods have this very particular form. So if you have this particular form, a quite natural idea is to say, okay, let's choose Y in order to minimize this distance, these guys, and just forget about F. And so you will have a very good kernel machine for every function defined on this data set. So if you try to solve this problem, it's a very interesting problem to solve. And if you are able to solve it, you will have the best interpolating machine or predictive machines. But the point is that it can be very computationally intensive to solve this problem directly. So we have some heuristic there if the data set is too large to solve this problem directly. We have k-means type algorithm that work with kernel distances. They can be very efficient on very large data set, but they will give you an approximation of this minimization problem. But they are quite. It works. It can be quite efficient. So
dear Mark,
yes.
So the kernel distances really behaves like distances in k-means algorithms, right?
Yes, you can consider them like. Indeed, you can run k-means algorithm and you can input kernel distances.
Instead of the normal distances that we use.
Yes, instead of normal distances, but take care. You have to take care to one point is that kernel distances are non-convex. So it means that you can run. So it's not really true for some kernels. Kernel distances are not convex. So you have to take care when you try to solve this kind of problem but because usually you start, it's a k-means algorithm and also this kind of direct approach relies on gradient descent algorithm. So you have to take care to the initial point because the distance is not convex.
Okay.
So this is an extra complexity that you would not find if you use normal distances like Euclidean one in k-means. But it works. It works.
Okay, that's good.
So the second family of method to tackle large data set as low rank approximation. Low rank approximation. The first idea is to somehow approximate your big kernel matrix by a smaller one that is here. So you are trying somehow to find a subset of your data set that best represent your kernel matrix. So this kind of approach can handle quite large data set, let's say medium. I've tried up to 100,000 data sets. It's okay, but it starts to suffer also because you have this guy here that is your size of your original data set to the square that is still too heavy. So I think that the most efficient methods that are found for large data set are what are called Nystrom greedy methods. They are very efficient for large data sets, but they are specialized to one function. So it's this kind of approach. When you use the first one, you try somehow to have the best approximation for any function. When you do this one, it's a little bit different. You are trying to best represent a function and not a functional space. So it's specialized to one function, and it's very reminiscent of important sampling for Monte Carlo method, if you know a bit this kind of method. So let us go a little bit to the strong point of kernel methods and their use in particular for partial differential equation. So as I already told a little bit earlier, what is very nice with kernel methods is that you can benefit of kernel differential operators. You can, if you have any set of points, you can define any kind of differential operation, and you can invert them. You can do a lot of you can manipulate them very easily. So you have access very easily to any kind of partial differential equation. One very convenient notion is the fact that kernel methods are basically meshless methods. You just consider any kind of mesh. It can be structured, it can be unstructured, but you don't need to maintain your mesh. You don't need to take care to the way it is numbered. So it means that in terms of development, it's very easy to develop with this method. And in particular, you can use this method in the context of particle methods. If your data set corresponds to moving point, it means that you move your point from one state to another. In the other state, you redefine your differential operator, and you go on to the next step. So this is a typical notion of Lagrangian methods to solve partial differential equation, and Lagrangian methods can be very performing. So another quite interesting feature of kernel methods for partial differential equation is that you can express very complex boundary condition quite easily. As you have an estimation of values of a function at the boundaries, and as it's a kernel estimation, it means that you have an operator and you can invert it to constrain your solution to a particular boundary condition very easily. And another quite important notion is the notion of explainability. That means the error estimation, because this error estimation allows you to enter into convergence analysis of your problems. So it means that you have all the tools that you need to analyze the convergence and complexity of the algorithms that you are designing to solve a particular dynamical system. And this convergence analysis, at my knowledge, okay, it exists for classical partial differential equation methods like finite difference, like finite volume, finite element, and it also exists for kernel methods. And indeed, kernel method use almost the same kind of approach as finite difference or finite element method. And but to my knowledge, these are the only methods that can provide a full convergence analysis to a problem. It means clearly that if you use neural networks for partial differential equation, it means that okay, you can run it to difficulties because you have no warranty of convergence, and indeed, most of the time, you will have approximate solution, but no convergence at all. So you have to take care. So this is why these methods are very efficient for partial differential equation. However, concerning kernel methods and partial differential equation, take care that if you consider finite difference or finite elements method for the low dimensional case, let's say up to the 3 dimension, usually finite difference or finite elements are more performing than kernel method. Why? It's very simple, because in finite difference or finite element method, you also have the notion of gram matrix, but the gram matrix is usually a very thin bandwidth. It means that you can have algorithms that are, and if you use kernel methods, usually the gram matrix will be dense. It means that it's faster to use a bandwidth matrix than to use dense matrix. So you are losing you are losing in the low dimensional case. However, there are some kind of there are some use case where kernel methods are, to my knowledge, the only methods that you can use to solve partial differential equation, and in particular in high dimension. If you go to up to the 3 or 4 dimension, then and above, I don't know other methods that can solve really partial differential equation with convergent results. In the low dimensional case, you can use kernel methods. For instance, if you want to fast prototype a solution, because kernel methods are very handy, you don't have to bother with match, so you can code very fast. Another use case are parametric PDEs. These are families of PDEs that depends on parameters, and so it means that basically you are solving partial differential equation, but with a dimension added by the dimension of your parameters. Or also if you have complex unstructured meshes, in which case meshless methods are very resilient to problem that occurs with unstructured meshes, like points that if 2 points start to merge, then your kernel method should be robust in this kind of situation. And there is also another quite natural usage of kernel methods that are PDE learning. PDE learning means, suppose that you have a very efficient numerical solver, like a finite difference scheme that is able to solve a complex, let's say, Navier-Stokes equation. But okay, it's very efficient, but it still takes a lot of time just to have one solution. What you can do is to use a kernel method just to learn the operator that takes your solution and move it to the next time step. So it means that you can learn these guys, and this guy means that somehow your kernel method will approximate the green solution of the green function of your problem. And this can fasten computation of classical scheme if you observe enough example of solution that is given by this classical scheme. So you need classical numerical scheme to learn from them. So I would like to show you some example of realization of partial differential equation resolution, and in particular in Lagrangian coordinates. So the first video that I would like to show is a simulation of type equation representing the solution of a particular particular stochastic process. And this stochastic process is called the SABR. So I will try to open my video. Where is it? It's here. Let's have a look if it works. So what is the simulation? We start at time 0 with a very concentrated pack of, let's see it again. We start with a very concentrated pack of particles, and we solve a bidimensional type, nonlinear type equation that that correspond to the density of this stochastic process. And what we are solving is a little bit more. We want to have the best approximation any time of this stochastic process with, let's say, I think it's 200 points here. So we want to have to each step the best approximation of the density of the stochastic process with, let's say, only it's an approximation of a probability measure with a discrete measure of 200 points, and we are trying to have the best approximation. So this kind of tools are very important. They are very important, obviously, for partial differential equation, but it corresponds also to find the best Monte Carlo samples. Yeah, and maybe if you know a little bit what are low discrepancy sequences as Sobol, Alton, etc., this kind of sequence, this kind of approach are will provide you with samples that are usually of better quality than low discrepancy sequences, but the drawback, obviously, is that they are computationally more expensive than computing Sobol sequences. But in order to also to illustrate the notion of boundary condition, I had some fun some years ago solving a Navier-Stokes. It's a Euler equation with viscosity. So here what you see are particles solving the Euler equation running into a pipe. So this simulation is done with very few points. I think it's 200. But so you don't see the pipe, but the boundary condition for Euler equation are a little bit complex. It means that the derivative of your solution must be tangential to the boundary of your pipe. So you can handle this kind of boundary condition very easily with kernel methods. So now let's go to now let's go back a little bit to kernel to statistical to machine learning algorithm. And this time I would like to speak about encoders and decoders. So don't be afraid. What is an encoder? What is a decoder? An encoder and a decoder between two spaces is just a mapping from a space to another. So if you deal, but when it comes to discretization, what you see usually as a distribution, you have two sets of points. Let's say y and x and y are two sets of points, and they can belong to unrelated spaces. It means that, for instance, the first set of points can belong to a space belong like r to the power d x, and y belong to rd to the and this is y. So, and they can live so in two unrelated spaces. So with kernel method, defining a mapping is very easy. You just take you just regress y with x, and you define just this operator, and this operator will provide you with a mapping that satisfy on x, that will be exact on x, and it will give you y. So that's the reproducibility property that I talked about some slides ago. But having a mapping from two space, it's different from having inverse a mapping that you can invert. And it's important in lot of application to define inverting mapping. So given any two distribution and defining a kernel prediction from one set to another. So the question is, under what are the conditions under which this mapping is invertible? So from a numerical point of view, it's all is a matter of finding a permutation between one of the two sets. And here the example is that I'm trying to find a permutation of the set Y. On this, sorry. So there are two kind of two cases. If you are considering x and y that are living in the same space, then the situation is quite clear from the optimal transport point of view. So it means that what you can do is just to find a permutation in order to minimize these guys, and this guy is a discrete equivalent of the Monge problem. And it will, if you solve this minimization problem of the set of permutation, then you will have the warranties that this map will define an invertible map from the space Rx to the space R1. And from an algorithmic point of view, this kind of problem are solved using what are called linear sum assignment problem. So they are quite, this kind of algorithm are quite optimized today, but it's still computationally intensive. It means that it can be difficult to solve this kind of problem if your data set is greater than 10,000. This is as a rule of thumb. So now there are a little bit more difficult problem. If the two space in which belong X and Y are unrelated, then the optimal transport literature is, let's say, a little bit more quiet on this topic. So, so this is why we develop an ersatz that is that have some similarity with the optimal transport tool, in the sense that we are just considering, instead of a classical distance, the classical distance is the kernel in this distance, we can, in this situation, consider a functional over the gradient of the set Y relatively to the set X. So doing so, we are trying, in some sense, to minimize the Hessian problem. And doing this, we are finding an invertible mapping, so from X to Y. And indeed, it is what is interesting for us is just to have inverting mapping. So these two approaches are not equivalent, but they are quite close. And this approach in particular is reminiscent of what is called the traveling salesman problem. And since we are considering, so the traveling salesman problem will be exactly this expression if you consider X taking value taking scalar values. But in this case, we are considering X living in this space. So this is why I call this generalized traveling salient problem. So the drawback of this approach is that it's much less known, to my knowledge. So I developed some algorithm, but the computational complexity of this algorithm are quite high, and it's difficult to use more than, let's say, 5 data sets that have size greater than, let's say, 5,000 in this approach. So what are the usage of such an approach? It's quite so the first usage are quite fun. So it means that you can take any two probability, and here in this example, I will take very strange probability measure. The set X will be a picture of cats, and the set Y will be picture of celebrities coming from a dataset that is called the celeb A dataset. So it means that if I have a picture of faces, and I can map them to picture of cats. And since the mapping is vertical, I can also map cats to faces. So it's quite interesting construction. So and this kind of construction for in the artificial intelligence community are called generative methods. So it means that we have also generative methods for kernel, and usually the name of the methods that are used with neural networks are GAN, generative adversarial network, or sometimes you have also WGAN for Wasserstein generative. You have some. So it means that it's quite interesting because here we are competing with neural networks. And neural networks are known exactly for this kind of application that are encoding from a space to another. So and here is an example of usage. So it's a fun usage. It's for illustration purposes. So it means that you can. So to the left, these are a lot of faces from the celeb A dataset, and it's not. I didn't plot them, but to each I associated a picture of cat. And then I took another picture of the cat, and using this picture of cat, I can generate other faces. And so these are the faces that has been generated by a collection of cats. And these faces, once you have generated them, you can somehow find what are the closest faces, but with the metrics that are given by the cats. So it's quite interesting construction. It's a fun construction, but what I would like to illustrate that these methods are not only good as generative method, they are also very good for pattern recognition. And you can imagine that this kind of mechanism can be used in other circumstances. But indeed, you can imagine that my company is not paying me to produce celebrity faces with cat. So our main field of application of this method are for time series prediction. So before talking about time series prediction, I would like also to give you another fun application of generative method. So I've told you, I have told you that we can take any picture and we can somehow regenerate. We can consider that this picture is a distribution that we can approximate with kernel methods, and so we can then have fun just to resample it. But now, if you consider that you have faces that has some conditional value, and in particular with its data set of celeb A, all pictures are labeled, and they have 40 labels, and among these labels you have hat and glasses. So in the first line here you have some picture of celebrities wearing hats and glasses. And what you can do now is it's a little refinement of generative method, is conditioned generative method. It means that you can take now your distribution and gradually toggle on or off any of your conditioned value, and your conditioned value in this example are hat and glasses. So I can have fun just removing hat and glasses from my celebrities. So as I told you, my company is not hiring me to toggle glasses and to generate faces. So in mathematical finance, one of the main interests of this method are for time series prediction. Here, so for time series prediction, it's quite easy to figure out what are the usage. You take any time series, and okay, here is a time series of three actions during 1 year, and the goal is, can you fit a model that have consistent prediction with this chart? So this is a quite important topic for mathematical finance, obviously. And in particular, we developed for time series prediction a kernel framework that use generative method. And the idea is to say, okay, consider any historical data set. You can map this data set using a function, and the function is associated to a given quantitative model. You can map so your historical observation to epsilon, and epsilon is a noise. So, for instance, the quite known model is the random walk model. You consider a time series, and you make the difference xt plus 1 minus xt, and you say this is the noise. So this is the first this random walk model is the first model, but all the quantitative modeling for time series in finance is built on this notion. All models correspond to a particular function. So it means that the idea with kernel methods now and generative method is that if you observe a noise, if you observe a data set, a historical data set, then using this function, you also observe a noise. And if you observe this noise with generative method, you can model this noise as a distribution, and you can resample it. If you resample this guy, then you define, using the inverse of this function, another time series. So it's quite this approach is quite interesting for mathematical finance. It means, in particular, that you are observing a noise epsilon, but if you consider exactly the same noise and you take f minus 1, due to the particular reproducibility property of kernel method, then you are generating your historical data set. And so it's quite, let's say, ensuring that your historical data set is in the scope and in the range of your model, at least. So, and now, if you consider another sample of your noise, so you generate another path, and if you, so it means that it's a framework for Monte Carlo, and it's a quite efficient framework for Monte Carlo sampling. And Monte Carlo sampling, if you have a Monte Carlo sampler in mathematical finance, you have access to a lot of other tools. And in particular, it is the basis to build powerful partial differential equation solver. So we are using this kind of approach in order to also to have access to other methods. So just to illustrate the fact that this is a very general model, we took any existing model, and a quite famous model is a model that is called ARMA. ARMA that takes two parameters. It's autoregressive models, and this this autoregressive model can be fit into this framework. So we just computed this function, and so we can use ARMA model in the context of generative methods. So it's somehow we are somehow extending all the existing quantitative models to generative method, and it's a little bit more deep than that, because as I told you just before, once I know a distribution in like the noise, now I can have access to quite to conditioning generation. It means that I can take another exogenous variable and considering that this guy, the noise, is conditioned by an exogenous parameter. So doing this, it means that I have a model that is not only adapted to historical observation, but that is also influenced by extra parameters that are observed and that is not part of the model. These are conditioning. So it's a very powerful tool in mathematical finance. So now I would like to somehow propose you some feedback on my personal feedback on kernel methods. Kernel methods are to my perception, they are very good to model mathematical physics phenomena. They are versatile, and it's a universal approach to interpolation, extrapolation mechanism. So it can handle very well partial differential equation, machine learning. So they are very handy to work with. They are, you don't need very deep knowledge to parameterize the kernel methods, but they are very performing, particularly for mathematical physics. For machine learning, they are also very good, and they are very good in the small to medium size dataset regime today. Why? Because as I told you, the large dataset problem is still problematic, and I think it's still under research today. So this kind of method are really interesting, not only for research, they are also very interesting for industrial purposes. The main argument for kernel method is reproducibility and error bounds. Why? Because when you work for industry, you need this tool for audit purposes, and they will be asked by your company for to have some guarantees that your predictions are correct. Another very good and very fascinating promise of kernel methods is their learning algorithm. Learning is just inverting a matrix, and it's a very fast learning procedure. And it's important to notice that today the whole artificial intelligence industry is stuck because of the cost of and the algorithmic complexity of existing algorithms. So it means that we could maybe provide alternatives that are much that are reduce the energy consumption of existing approach to intelligence artificial. So, but as I've told you, the landscape is not bright everywhere. So the first point is that this method still needs research to be used in some case, like especially the large dataset case is still problematic today. So above all this, I think that the main drawback of kernel methods is that there is no standard library to use this method. So we develop our own library. It's open source, but we are a small team. It's not a professional. It's not intended to be professional, and we lack of resources to develop it. To be honest, so so we have one let's say one framework, CodePy, but you have also other actors. You have scikit-learn, TensorFlow, PyTorch. You have also Keras. I surely miss a lot of them. But among all these frameworks, there is still not a proper definition of what is a kernel in a library. They all will use different concepts, and they are not interoperable. So that's a real problem if you want to develop professional solution. And okay, I think I will end this talk giving you some references. First of all, so as I told you, all what has been presented during this talk has been made with our only library. So I give you a link toward our book. Our book is a little bit more than a book. Indeed, it's our user manual. It means that all the book is made with LaTeX and Python, which means that you can use the Python to see how each algorithm has been written into the book, and you can learn it. And the main intention of this book is to be a user manual, and also gives you a link to the book because it contains at the end a lot of references of. So you have surely noted that I didn't quote anybody during this talk because okay, there are a lot of people that I should quote. So please have a look to the end at the bibliography. You will see the main authors dedicated to kernels. And so I just gave some names of people that I read very often, like Thomas Alliance, Mola, Jacob, Bernier, Greton, but there exist many others. So I think that's all for today. We'll stop here.
Thank you very much, Professor Mercier. That was a very nice talk, and I personally learned a lot, especially in applications, and I have a couple of questions also, but first I want to ask the audience if they have any comments or questions so that we can spend 5 minutes or 10 minutes for Q&A. Bülent Hocam had some questions, I guess, at the very beginning.
There are here some, the kernel methods are used by identification of physical models or systems, especially, for example, like Hamiltonian systems or structure preserving systems, and so how the code pi can be extended or applied in this direction for identification of from the data to identify that it's a Hamiltonian system, or I don't know whether another one is something like this.
So, I'm using also kernel methods for Hamilton-Jacobi type equation. If this is the question, I'm not sure this is your question.
My question is now, when you have a data and then you know that is fits now to Hamiltonian differential equation, quarter-vector Fourier equation, nonlinear Schrödinger equation, and so on. And then by kernel regression, you can now find now the Hamiltonian structure, then preserve the structure, and then find the system. I think code pi can also be now in this direction, can be applied. So then here the kernel methods.
Okay. Okay. So it was not really a question. You're saying that you can you can approach the green function with with kernel methods. I'm still not sure to understand your question, but if this is if it's your observation, I totally agree.
No, actually, how can we use, especially in your talk, you said learning PDEs. So that's
Yes.
data-driven dynamics governed by partial differential equations could also be applied, I guess, using kernel methods.
Yes.
Yep.
Yes, and the idea is very simple. If you know the solution of your equations, then you can, from one step to another, you can learn somehow
Yeah.
transformation. And this just observing your solution at each step. And doing this, it means that you will approximate I'm missing the word, the green kernel of your
Yeah, I would say that you are
Sorry.
learning the kernel.
Yes,
Especially the greens kernel. Yeah.
Yes, yes, and you can do it with any kind of equation. And indeed, it's not kernel methods are not the only one methods doing it. And in particular, maybe you have heard that recently Google has been able to provide weather forecast very very fastly, and the fact is that Google just do exactly what I told you. They are observing a solution of very computationally expensive solvers from one step to another, and then they use a sensor just to map, and they just approximate the evolution operator of a weather landscape with a lot of examples. So they have a huge data set, and this is the way they are doing. They are doing it with neural networks. We are doing it also with kernel methods.
Okay. Any other question? So I see our Özkan değerli hocam. Özkan there. Oh, hi. So I would also, I was wondering when you mentioned in autoregressive moving average models, in those applications, especially when predicting time series, have you ever come across to combining special kernels for different parts of these time series, the autoregressive part and the moving average part, two different kernels, or just use the single kernel?
No, yes, that's an interesting suggestion, but no, I just use one kernel. for.
Yeah, because the sum of two kernels is a kernel.
Yes, you're right.
So
You're
this
right.
is
I never thought about
this
it.
could be quite interesting,
Yes.
especially when defining the parameters P and Q in the ARMA process and even in the Gauge process as well.
Yes, yes, right. Yes,
One thing.
the ARMA example was just here to illustrate the fact that you can consider any quantitative model, and it's one type among others. But you're right. We could refine this approach.
So, what are the applications of convolution kernels, especially in PDs and time series? Are there any?
No, well, to be honest, I developed this kernel for one reason only, is for image recognition. You know, if you want to look to a pattern to an image, then if you want to identify a cat, let's say, the problem is that the cat can be everywhere in your image. So if you don't use convolutional kernels, so the result can be a little bit will not be very good. But if you try to match your cat image somewhere in your images, then you will have better results. This is this kind of remark that has been used by Lequin for convolutional network. So we are doing exactly the same for kernel methods, and for kernel methods we are using another trick that allow us to have very fast algorithm. Is that convolution can be estimated very fast with fast Fourier transform.
Even faster than fast Fourier transform?
Yes, so we are using convolution instead of computing a raw convolution. We are computing it using fast Fourier transform. That means that we are very fast algorithm for pattern recognition today with kernel methods.
That's great. Okay, that's all my questions. Anybody else wants to talk, comment? Hi, our director, Seftap Kestel, Professor Seftap Kestel, has arrived. I can give the final word or just finish the talk or the recording first. Maybe I should stop recording and then we can discuss a little bit more. And I really wish to thank Jean-Marc Mercier for this very nice talk.
Ömer, may I ask?
Yes, sure. So, Jean?
I have a question about, in complex analysis, we have some, I am interested in some differential equation and partial differential equations, like Loebner differential equations, such things again. And then, is it possible to apply there this technique, the reproducing kernel Hilbert space? I don't know.
Okay. Yes. So maybe I should have a look to the equation that you are trying to solve. But I would say that there is no all what you can do with classical method you can do with kernel methods. But just to take care that kernel methods can be less performing classical methods in some cases. But yes, if you send me your equation, I can give you some advices if it's pertinent to use such a technology for the equations that you consider.
Okay. Thank you.
Okay, thank you very much again, Mercier. So I'm stopping recording.
So
Can
Okay,
we
thank you.
send follow-up? I'm sorry.